Hi guys, I'm Shmee, hello and welcome back to the channel where today you join me at the home of Rimac. I'm just outside Zagreb in Croatia and today we're going to be going for a complete factory tour, a full visit with none other than company founder Mate Rimac himself. We're going to be seeing the likes of the Concept 1, their newly introduced C2. We'll be exploring the assembly of the cars, taking a look behind the scenes at the design, the manufacturing of components, the carbon fiber usage, the engineering, and there are a lot of simulations that they're running, believe me. We're going to be fully discovering today the home of Rimac, so let's head indoors and get started. Here we go then, Mate, how are you?
Good, Tim. Thanks for coming to Croatia.
Thank you very much for having me. I've never previously visited. I'm very excited to be here, and what a setup.
Yeah, thanks. We are very proud of what we have built, but we are also very cramped and because we have grown so much. So yeah, it's a little bit, everybody's very tight.
Well, I hear exciting things are also coming for the future. But we're standing in your welcome reception area, and we can already get a little hint about what we're going to be able to see today. So can we take a look around and have a chat about what we're looking at?
Yeah, here, well, this is a little bit a display of our history. Like this is the first car we built. In 2011, this was the car we showcased in the Frankfurt Motor Show. And back then we were 6 guys, had absolutely no idea what we were doing. Before that, I just did the green BMW and the whole story how it started. And since then it's been a long journey. So since then we evolved to a technology supplier to the other car companies. So we can also see a battery pack for the Koenigsegg Regera or a battery pack for the Aston Martin Valkyrie. And the company has transitioned now to go into more high volume stuff, also with our supercars. So we have a C2 Aerobac here. So this is the wind tunnel model, a one-to-one model, where we change stuff and test different layouts and compare it to the computer fluid simulations. Here, what you'll see here today is basically everybody is now working on getting the C2 into production. So it's our new hypercar. You can look at the Concept 1 and say, okay, that's an electric hypercar, and the C2 is one as well. But it's like light years apart, both in performance but also in everything else. So this is going to be produced in 150 units, just a coupe. We have models coming later as well. The performance figures are quite crazy, 1.4 megawatts, which is 1,900 horsepower, 4 electric motors.
I'm just going to quickly interrupt. 1,900 horsepower.
Yeah.
The numbers are a little bit crazy, aren't they?
Yeah, exactly. Well, it's the most powerful production car ever. And it's much more than about the numbers. We wanted to make it very comfortable, very usable, like on the level of big car manufacturers. So not like a garage project, but a real proper development program. So we are developing it for the global market. So doing all the global crash tests. We unfortunately have to crash a lot of cars. So we are producing 25 to 30 prototypes at the moment. We are still deciding the exact number for all the hot weather testing, cold weather testing, US impacts, EU testing. So we are doing the full program. And it's being developed from ground up, so we have zero carryover from the Concept 1 or for other cars, which is very unique in the industry. Usually everybody starts with something, with the powertrain on the platform of another car, previous models. This is from scratch. So it's a very special project. And on the other side in the company, there's lots of stuff going on, working for other car companies. We just announced the Hyundai and Kia investment. Porsche is a shareholder, and the stuff we do for others.
Yeah, so you were saying this is battery pack for the Valkyrie, which is rather tiny.
Yes, well, that's a hybrid car, so that's not a lot of power, not a lot of energy. So this is 130 kilowatts, so that's more for a boost. But this is actually the highest power density battery on the market. So for example, the Koenigsegg Regera has 7 kilowatt per kilogram battery pack. 7 kilowatts per kilogram. Yeah. So a lot of power in a small space and not a lot of weight. And if you look at the 5 electric or hybrid hypercars that are coming to the market, 4 out of those 5 we are designing and producing here. The batteries for them. So. Okay, impressive. So this is a very nice way to arrive, seeing the first car, your R&D vehicle, the wind tunnel testing C2, but the adventure continues. Yes, let's go. Let's go have a look around. We are here in our vehicle assembly area. We are producing the bits and pieces of our car all around the company, and then we put them together here. This is a fun one, so you had actually the opportunity to experience this in the Goodwood Festival of Speed. I was going to say, that's the customer car I went up the hill climb in, right? Exactly. That's one of 8 customer concept ones. And we are just in the final assembly of the last 3 customer cars. So
Oh, wow.
These are made for the customer. The last 3 concept ones.
Okay.
So the one there, the bare chassis basically is the last one.
Yep.
And here at the same time we are assembling the C2 prototypes.
Okay.
So these are prototypes, the monocoques we are now putting together. Actually this one, unfortunately, is going to be crashed in a couple of weeks.
Oh no.
So this monocoque will die soon.
But I mean, it's critical, right? Crash testing is a vital part of getting the cars onto different markets.
Exactly. So this is developed as a full globally homologated car and as a platform also for our future projects. And it's really unique. So this monocoque is something special. It has the highest torsional rigidity of any monocoque that I know of. So it's 80,000 Newton meters per degree.
Oh wow.
It's one piece. So the front suspension and the rear suspension are actually on the same piece. So other supercars or hypercars, they usually have a subframe which starts here, and it's either steel or aluminum or carbon. But this is really one piece. So the rear suspension is on the same part. Then we have the front and rear crash structures, so they are deformable. And in all the crash tests, only the crash structures should deform. There's only one crash test that will write off the monocoque, which is the pole impact.
Okay. Yeah. So just to clarify, the entire cage over the top, the rear section, the front, it's all one single carbon fiber monocoque piece.
Yes, the roof is bonded and bolted. Everything else is one piece. And just to give you a sense of complexity, so this is the top is now one piece, but it's actually 2,200 carbon fiber plies. So 2,200 carbon fiber pieces arranged in exactly the right direction, in the right sequence, different materials. We have also all kinds of different inserts, carbon fiber inserts, aluminum inserts, titanium inserts, honeycomb, all this stuff in there. So it's a really, really complex part. And it has a completely structurally integrated battery pack. And the battery modules in the battery pack are a structural part, and even the battery cells in the battery modules are adding to the structure. That's why we have such a high torsional rigidity. And the front and rear powertrain are also inside the monocoque.
Yeah.
So only the crash structures, so here's the front crash structure. So in the worst crash test, which is the 64 kilometer per hour full overlap into a wall, into a rigid barrier, this crash structure collapses all the way until here, and the remaining of the passenger cell and the monocoque is not deforming.
Wow.
So we are doing lots of tests with one monocoque. We crash the car, repair it, remove the
crash structure.
Crash structures and so on, and then crash it again, and then the last crash test is always the pole, where then the monocoque is right.
Yeah. So this is all in the pursuit of, well, carbon fiber, lightweight, of course.
Exactly.
Strength, rigidity,
and safety.
And safety
is primarily, the target for this project because we wanted. So you can develop a hypercar in several ways, and the concept one we did when we really didn't have any idea about how to do stuff like this. We had learned along the way. We didn't have the financial resources, we didn't have the experience in doing this in Croatia, where nobody has actually done anything like that. So in the last 10 years we have built up the experience with all of our projects that we have done and built up the team. And from the 10 people we are now more than 500 people. And
that's incredible.
With all the investors on board, we have now completely different ways of doing things. So.
And that's all happened in a very short time space, right? When did things start up? When did the Concept 1 start up?
Well, I founded the company officially in 2009. I started with the BMW earlier, like in 2007 and 8. And the first employees joined me in April of 2011, so I consider the company really to exist 8 years.
Wow. And you're now working on engineering like this?
Yeah, well, and that's really special because absolutely everything is developed for this car. That's such rare in this industry. So let's say, for example, the front and rear powertrain are completely different. So the front architecture of the powertrain is totally different than the rear. Why? Because it's optimized for the specific purpose. So the monocoque, the suspension, the powertrain, the gearboxes, the inverters, the electronics, everything was developed specifically for this car, no carryover. So that's why everything was optimized to achieve this target. Just like one figure. So this is more powerful than a Bugatti Chiron. It's 1,900 horsepower. It has a 700 kilo battery inside. Yeah. And we want it to be the same weight or lighter. We are currently a little bit above the target, but we are working hard to reduce it. So with the 700 kilograms of battery, we try to be lighter than the Chiron.
Okay. So, I mean, just looking around here, it's particularly interesting. It's literally how, as you were saying, the components are all bolted straight to the top, the suspension components and the arms.
Exactly.
That's quite an unusual thing to be looking at.
Yeah, some hypercars, they end their monocoques here, and then they have a subframe from here, which makes it easier and cheaper. The same thing for the rear. We wanted really to have this rigidity and really a very, very stiff structure, so that's why it's all one piece. And then the structure has also some interesting other things, like the packaging. We didn't want the battery in the floor, because that would mean that the seat goes up, which means your H-point goes up, which means the roof goes up, which means your frontal area is bigger, which means your aerodynamics are worse, and it doesn't really look like a hypercar anymore. So we don't have a battery under the seat, so we have part of the battery actually under the feet here. And that's also to get more weight to the front, to use the torque of the front powertrain to have more grip on the front wheels. Then we have a battery in the tunnel and in the rear of the car. And the battery is actually now mounted in the monocoque, so you can actually see it a little bit through this hole.
Ah, okay.
Yeah. And then we have the big cutout that you can see here in the roof. So we wanted really to make a very usable car. It's not like just to stand in somebody's garage and collect dust, but we really want people to use it. So when you open the door, it's really easy to get in and out, but you don't have the structure here. So we had a lot of structure in the top to compensate for this. And then you can see the top is going inwards. So if you had the wheels on the car now, you would see that the top is actually very far inwards compared to the outside of the car. And we did that so that you don't have to put your bottom on the sill to get in or out, which is usually the case with hypercars.
You can swing your leg and kind of step in.
Exactly. So while you are sitting in the seat, you can put your foot down on the floor, which seems like a very simple thing, but like to achieve that, to have such a narrow monocoque here, there was a lot of work to make.
I can imagine.
And then in the rear we have, so you can't even see it really. So this is the inverter of the rear powertrain. So below that we have the gearboxes and the motors. So we have 2 motors and 2 gearboxes and 2 inverters in here. Everything specifically designed for this car. And this is actually 1 megawatt rear axle. So this is 1,300 horsepower in the rear and another 200 kilowatt on each side in the front. So in total 1,400 kilowatt. And this thing here is converting the DC energy from the battery that comes out here into the AC current for the electric motors. And we have separate cooling systems. So we have a cooling system in the rear. So here actually the cooling system of the rear powertrain comes here. And then we have a separate cooling system for the front powertrain. Because we didn't want to have the piping all around the car. But the difficulty with that is the front is in the airflow. So it's easy to cool it. While it's really difficult to get the air in back here. But 80% of the load is on the rear axle. So you need to get all the air here to cool the rear powertrain system. So that was quite difficult and a challenge to achieve. So we have done so many simulations and iterations to get the aerodynamics and the whole package right.
I mean, that's a big part of what we're going to go and see next, isn't it?
Exactly.
The engineering and simulations that go into creating all of this.
But that's actually the advantage of doing everything, all the engineering under one roof, because we make trade-offs on everything. Like, just to give you an example, so here you have a certain space, you have the width of the car, and then you have a certain space for the suspension, you have a certain space for the structure of the car, for the monocoque, you have a certain space for the motors and for the gearbox. And when you want to optimize a system, it's always a trade-off between those things. And if you want to achieve a sub 2 second 0 to 60 acceleration, which we wanted, there were fights for every tenth of a millimeter between those systems. So do we give more space for the suspension so you can have longer suspension arms and a better geometry? Or more space for the monocoque to achieve the crash targets easier? Or more space for the gearbox so you can play with 2-speed gearboxes and stuff like that? Or more space for the motors to have a more active length in the motor? So like, whoever says there is no compromise, that's a goddamn lie. You are compromising on everything, and when you have the freedom to compromise on everything and all the people are in the same room, I mean, somebody has to orchestrate it to make the decision where the priorities are, and in that case I was that guy. But with that we could really optimize the whole thing. So it's really difficult, I think, to push the limits further because everything was so tightly developed together. So this is the Concept 1 frame. It's actually chrome molybdenum chassis which is welded. It takes like 2 months, 2.5 months for our guys to weld it. And as you can see, it's not a monocoque, it's very different. So the battery pack is in here and in the tunnel, it's like a T-shape, and then the rear powertrain is here. And if you look at it, so you know, when we were doing this, we didn't have the funding to have an autoclave. We didn't know how to develop a monocoque, you know, and stuff like that. So both cars are electric hypercars, and this was the first proper electric hypercar.
Yeah,
and
really
it was
was
very significant in terms of the achievement for that time. But you know, we have gone so much further. It's like light years between those two cars.
Yeah.
And you know, when we look at it now, we are a little bit, you know, ashamed of what we didn't know back then when we.
I don't think you need to be ashamed of it. This was a massive step ahead of the time, as you say, the first real electric hypercar.
It was, but still a long way to go from here to the C2, and that's what we have been doing basically for the last 8 years.
So, of course, a lot of the C2 revolves, excuse me, around the carbon fiber components and bodywork and things that you're doing. So, can we continue on and go and explore?
Yes, let's see how that all comes about. First on computer screens and on processors, and then later in reality.
Sounds good to me.
Okay. Before stuff turns real, we actually design it here and engineer most of the stuff. So this is part of our engineering, and our engineering is divided in 2 areas. This is the vehicle engineering, which is developing the cars, our own hypercars. Upstairs is components engineering, where we develop all the batteries, the motors, and the stuff we do also for other car companies. So here's like 70 people, and they are all still working on the C2. And I can show you a few things that are quite interesting to see.
Okay.
So let's go first to the vehicle dynamics and simulation class. So in order to define, for example, how much batteries we have in the front and how much in the rear, like what's the ideal distribution, we do lots of simulations. So this looks like a nice low resolution video game, but it's actually much more. So we do something which is, so everything is modeled, and that's quite interesting. That's something that some other car manufacturers don't really do to that extent. So we have a model of absolutely every part of the car, which means the suspension geometry, the tire model. So we have a mathematical representation of the tire's physical characteristics, of the battery pack, of the cooling, of the aerodynamics, of the active aero, of the tracks, of the software in the car. Like absolutely everything is represented in the model. And we can try out thousands of different or millions of different setups and combinations before actually producing a car. So that helps us to optimize it like to 98% before we build the car. So what you have here is a car running on a track, and what it's doing is actually we have the real software of the car in there. So this is called software in the loop. So for example, you can see the torque on each wheel, and here in this model we're running the torque vectoring software, and we are simulating to the software what it would actually get in the car. So the throttle position, the steering angle, the yaw rate of the car, the G-forces, the suspension travel, absolutely everything. So for the model, for the software, for the torque vectoring, it feels exactly like it is in the car. And we can tune it and set it up in a different way and simulate also things that might not be safe to do in reality. So when we do it in reality, we have a car that's already quite there, you know, quite close to where we want to be, and then also already safe to some extent, and we know how the systems work together. So for example, the trade-offs that we are doing now, for example, is to get laps on the Nürburgring, to not overheat the battery, like with how much power do we really go, how much do we limit the power that we don't reach the temperature limitation, how do we activate the active aerodynamics and stuff like that. So to have, when we go on the track to test this, that we are already quite there. Because in reality you can only tune so much, and in this stage you can tune a lot more.
So here, I mean, just what I'm looking at, speeds of course, but you're seeing the battery usage with different performance inputs. Is this simulating going around the Nürburgring at the moment?
Yes, this is a Nürburgring, and then we have all the data, like how the battery temperature increases, or like how the motor temperatures behave and stuff like that, how much energy we are using, all of the stuff. I mean, and for several systems, for different systems, we have different simulations. So I can show you another simulation, for example, the structure. So you saw how the monocoque looks like and the crash structures. And this is the result of millions of simulations and supercomputers running for years to simulate that. So for example, we have to simulate the crash model, we have 6 million little elements that have to be simulated because, for example, for the monocoque, we have every layer of carbon fiber, every piece of carbon fiber, every aluminum insert, everything is in the models. So I can show you how that looks like, just some examples. So even stuff like this, so for safety, you have to do tests of the head impact. So we have these structures, which are the buttons in the car, and when you bump your head against it in a crash, there is a certain load you cannot exceed. So this is actually engineered to compress in a crash. Or when you hit it from above, there is a structure behind it that is exactly designed to brake in a certain way so you don't injure yourselves.
Wow.
So we do even stuff like that. Or here in this case, so you can see the monocoque of the car, and every layer of carbon fiber is modeled there. And this is the result of, like, this is not the first iteration, there were like hundreds of things already done. Let's see the front impact, which is one of the most difficult ones. So this is a 64 km/h full front impact. So here the idea is that the front crash structure collapses and the monocoque stays intact. And this looks like a nice video, but it's actually 6 million elements being simulated in a supercomputer for hours. And just remove the front parts. So just to see how the crash structure compresses.
So that's what we've just seen is basically how all of the energy of the incident would be absorbed up at the front.
Yes, exactly. So we have the front beams and the cooling system, and all the important bits are behind it. So the powertrain and the gearboxes and stuff is behind it inside the monocoque. So when we run the simulation again now, we can see how this all energy is being absorbed by this structure. So you can see how it collapses. Then we can see the same thing in reality. And how the simulation doesn't really always correlate with the reality. So this was the first test we did, and you can see how the rails are peeling like a banana. So this was the lower speed, so they peeled like this. So we had a problem, and we had to figure out, like, why did this happen? Why didn't it collapse like it should have? And we have done lots of simulations and like to understand the material and like why this happened. Then we made several proposals and several changes, and went to test again a few weeks later. And then after that, we got this results. And you can see here it behaves exactly like in simulation. So we have now very good correlation between the actual results and the simulation. But sometimes, you know, of course, you have to do the real physical testing still to have like because it doesn't always correlate 100% because it's such a complex system. There's so many things that can go wrong, like wrong heat treatment in the material, like assembly process differences, or like material characterization. Like to get all of this so that the computer knows how the parts will behave, you have to have the right material properties, which is especially difficult with carbon fiber because it's not a solid material. It's a lot of layers of different materials on top of each other, which have different characteristics. They have different absorption characteristics in different directions. So, for example, you have a unidirectional carbon fiber, which takes energy only from one side, and if you have it in the wrong angle, it might not work. So, in the end, you are doing the real test. But when you are doing the test, you have gone through a lot of simulations to make sure that you are already almost there.
Fascinating.
Making a car look nice is one thing, but making it work with all of the different aspects it has to do is another. So one very important aspect is, of course, aerodynamics. So every surface you see on the car has been changed and modified, maybe sometimes for just a part of a millimeter, hundreds of times to fulfill all the requirements. So here what we see, for example, is how we guide the air around the car and through the car to get the rear cooling. To get the target. So at the beginning of the project and later through simulations, we had targets for every aspect of the vehicle. One of the aspects was how much mass flow we need to get into the rear radiators, and that starts already at the front. So when you make a change in the front, or for example in the brake system or in the suspension or on the wheels, it impacts the rear cooling. And especially it's important how you get the air out in the end. So as I said, the front powertrain is in the airflow, but it's not having a lot of load. The rear powertrain has lots of load, but doesn't have the airflow. So it was really difficult to get the air into the rear, and that was one major area of the development here. And being an electric car, we are limited by the energy we have in the car and recharge time and so on. So it's really important to get efficiency high. So we have active aerodynamics, and depending in the mode you are in, we have more downforce or less drag. And we are trying to get as much downforce with as little drag as possible, of course. So in low drag mode, we have a drag coefficient of 0.28, which is really good for a hypercar, with so many air vents and openings and stuff. And absolutely everything on this car has a purpose. So every square millimeter has a purpose. It's quite easy to make a nice looking car if you don't have to fulfill global crash homologation, active aerodynamics, drag and figures and so on. But this is really like a nice, in my opinion at least, nice looking car, which is fulfilling all of these targets.
We've come into the next stage where it's a little bit louder.
Yeah, here we are making stuff actually. So there we design it, and here we make it. So for example, carbon fiber parts, how the process goes, we design stuff, and design is a lot more complicated than you think. So there it starts with concepts and surfaces and 3D models. Then we engineer it, do the simulation loops and optimizations and go back and forth. Then we do the production engineering, then the tool development. We make the tools here, so the tools for the carbon fiber are made here, and then we use those tools to make the carbon fiber pieces, which you will see later. So from the white sheet of paper until the carbon fiber part is on the car, it never leaves our buildings.
Wow, okay.
So there are like 300 different tools that we make for the C2. Some are big ones, like for, I don't know, the bonnet or for the door. Some are really small ones, and we make either positives or negatives, but I will explain that a little bit better later. Okay. And then here next to us, we are making actually the bits and pieces that go into the car and other parts that we are doing. So this is machining, and here we start with blanks of aluminum or copper or steel or even plastic and make thousands of different pieces. So the guys are now just making like, this is the block we start with, and this is like a bracket to hold something. So this is quite a simple part, but there are like a million different parts that we are making. So this is holding the rear powertrain in place, so connecting on one side to the monocoque, on the other side to the powertrain. Or here are the buttons in the car, which we saw being simulated hitting the head against it. Or a gearbox housing, or like a cooling distribution part, or motor part. This is actually to cool the rotor of the motor. Copper part, actually this is for the Aston Martin Valkyrie battery pack. Okay. Or this is a door handle inside the car, so this starts as a huge block of aluminum and is milled down to this little piece. Yeah. Or a mold for carbon fiber. So it's like so different, and you know, we start with a block of aluminum, and that block can end up, like a piece of it can end up like a button of the C2, a piece of it can end up in a Koenigsegg, a piece of it can end up in a Porsche, whatever. So we develop the system, we make the little pieces, and then they are assembled in different assemblies for the battery, for the powertrain, or the suspension or whatever. The tool is producing the tool for producing a piece of a system. Okay, the tool is producing a tool that produces a piece that goes into a system. Yeah, which is part of the car. It's a long process. Yeah. So we actually have a department which is called industrialization, which is taking the designs and the parts that we want to make and then develops how we actually do the parts. Okay. So if it's on a production line or something like this, if we machine it or mold it or injection mold it or sandcast it or whatever, and we figure out the best methodology to do it. And then how to assemble the stuff. Is it in a nest production? Is it assembly stations and stuff like that? We are here in our composite department where we make here first the tools. So the tools come in different forms. So this is what you saw being made on the machine. So this is like a positive tool pattern, which is not the tool where we actually machine the part. So out of this we make a carbon fiber tool. So the carbon fiber tool looks like this. And the carbon fiber tool is better because it has the same coefficient of expansion when you put it in the autoclave and it heats up, like the piece itself. If it's a different material, you have to account for that because this is expanding differently than carbon fiber in the autoclave. And also this can only produce a few units, while here you can make hundreds of units. So this is good for prototypes and to make the tools, while this is actually for production. But in some cases, we make a direct tool in negative into the into aluminum. So this is an aluminum tool for a rear mirror, and as you can see, it's two-piece. So why? Because when you laminate the part, you know, the carbon fiber is like a fabric. But once you put it in the autoclave, it gets stiff. So it has the undercut here, so you can't take the piece out anymore. So you would have to destroy the tool. So that's why the tool is dividable. And this is a really simple example. Now imagine a big piece, like the monocoque or the bonnet. So the tools get very complicated. So it can be that a single tool for a single piece is like 20 parts which you have to remove. Okay, so it's a whole
mechanism itself.
Yeah, the tool itself, you have to engineer the tool.
Yeah.
And then, you know, we engineer the part, we design the part, we engineer the tool, we make the tool, we make the part.
Yeah.
And the other case, like when you don't do a direct mold, is if you do a positive. So this is a simplified example. So you mill the positive, and then you make the carbon fiber tool. So you use this only once. Okay. Or if you need more tools, you use it a few times more. So you can do different things. You can do a direct tool into this, but then you can only make a few prototype parts. You can make a direct tool into aluminum, but that's more expensive and more complicated, which is okay for small parts, but not for large ones.
Yeah.
Or you make a big positive out of this material, and you make a carbon fiber tool.
Okay.
And then, out of these tools, we laminate the parts, which I will show you now. We are here in the lamination, where we first cut the carbon fiber pieces. So this machine is taking the roll and then cuts the different pieces for lamination. And we have lots of different materials.
Yeah.
This is composites, it's not just carbon fiber. And carbon fiber is not carbon fiber. There's lots of different carbon fibers. This is just a small selection. So we have different carbon fibers. We have glass fiber, we have Kevlar, inserts like honeycomb, and like copper sheets. So why? For example, we make not just the visible parts of the car, but for example, the battery packs, housings are also made of carbon fiber, and they need to have electromagnetic protection. And for electromagnetic protection, we use copper sheets, which are laminated inside, but you cannot put the copper sheet between sheets of carbon fiber because carbon fiber is electrically conductive, which means it will come to electrical erosion between the two different materials. So you have to put insulators between, which is the glass fiber. So, and then for penetration protection, for example, if the battery is in the bottom of the car, you don't want something to penetrate through the bottom of the car into the battery pack. You have Kevlar. Okay. So in one piece you can have lots of layers of different materials, which are in the end look like one piece, but it's actually much more complex.
It's not just the visual carbon that we're more used to.
Yeah, this is just the first layer.
Yeah.
So one piece can have like one layer or two layers on one side, and on the other side, where it's structurally important, can have more than 20 or 30 layers.
Okay, wow.
So, and you have different kinds of carbon, like basically this is plain, so this is just like the fabric, there is nothing in there, there is no resin. And then you have pre-preg, which comes already with the resin inside. Okay. This is what we use mostly. And this is what, for example, is used for Formula 1 and for other applications as well. And then you have different grades of carbon fiber. So you can see this is more a fine mesh, this is more of a like a bigger mesh. But you have also structural materials that are just unidirectional, for example. So it takes load only in one direction. So it's very important how you put the layers together and in which angle. If you put the layer wrong, if you put the angle wrong, you can completely destroy the part. And like if you have a crash, the car will behave totally different than it was designed for. Okay. So once the materials are cut, so basically what we do from a 3D model, like a 3D shape, which is, for example, a wheel arch or something like that, we put it on a 2D surface, and then the machine decides how to cut the parts to reduce scrap as much as possible. So you use the material to the highest degree. And then the laminators get the laminations to laminate the part. So let's see some examples here. The guys are actually now doing, this is actually the mold for the rear bumper of the C2. Okay. So this is the positive pattern under it. So the milled block, which is a huge part. And then we laminate the composite tooling on top of it, which is how many parts, how many pieces? 6. Yeah, so 6 parts that you have to take apart because of the geometry of the part. Because, for example, you have here like a hole to put the sensors inside, which have a negative undercut, so you have to remove that part of the mold to be able to put the part out. Or something completely different, like here, for example, is the Koenigsegg Regera battery pack housing, which is being laminated. And this is actually this unidirectional material. So you can see it doesn't have these weaves, like this is a normal carbon fiber that you are used to, but this is just unidirectional. So all the fibers are going into one direction. And then in here you have all of these different layers, different materials, being laid actually into a carbon fiber mold. So this is actually a carbon fiber mold. Then once this is done, it gets in a vacuum bag, so the air is being sucked out of these tubes. Then it looks like this. So the tools with the carbon fiber laid inside already, and then afterwards it goes into the autoclaves. We have a small autoclave here for smaller bits and pieces, and a big one here for the largest parts of the car. So here the guys basically laminate during the day and prepare all the parts, batch them up together, put them in the autoclave during the night, and also different parts have different curing cycles, so different pressures and different temperatures over time and different cooling cycles. So you have to match that up.
Yeah.
And then this is a lot of energy. It's 300 kilowatts just to heat it up. So that's why we do it overnight when the machines are not working. And then the next morning they are pulled out of the mold, cut, because you always have like extra material. They have to be cut. Sometimes they have to be bonded. You have to bond several parts into one. Then they go either to upholstering or leather or alcantara or whatever. Since I'm a vegetarian, I'm trying to get people not to use leather, but the customer chooses. Or they go into painting and then into assembly, either of a battery pack or of a car or another part. So from here it goes to the other departments and then onto the final assembly. So this is how the final parts then look like. Like for example, this is the front light of the C1, one of the parts. So it has sharp edges. It needs to be cut either on a machine or by hand, depends on the number of parts and the complexity. And you can see here, like some of the parts are not just simple carbon fiber. They might look like that from the outside, but inside they have other structures and even some other carbon fiber pieces or metal pieces. So it can be quite complex. Or there are parts not of, like here, this is for example a part of the Concept 1, which you can see from the outside. But sometimes the parts we make here are parts of other parts. So this is for example part of an electronic control unit. So this is just the top of it. But for example, in the battery pack, we have composite parts that are so the composite housing of the pack that you see from outside, but also composite parts inside. So for example, the battery module housing or stuff like that. So we use composites for a lot of stuff, not just the stuff you see from outside.
For sure.
There's hundreds of parts, hundreds per car. This is our dyno, where we test our powertrains, and this is the Concept 1 rear axle, which is basically two motors. Each is 330 kilowatts and 420 newton meters, and they are connected together to be the load for other motors. And this is the C2 rear axle prototype motor. So we wanted to get the same space, so like the same volume, diameter and length, same weight, which is 50 kilos, but much more power and torque. So now one motor has 500 kilowatts of power and 700 newton meters of torque. Wow. And we are trying to increase that even further. So in the same package we have a lot more power. And what we also wanted to get rid of is, in the old motor you can see here, we have something like a sump, and which has oil in it. So the motor is cooled by oil, so the oil goes through the rotor and stator, and then you are cooling the oil outside of the motor with a heat exchanger with water. Okay. So you have a heat exchanger, you have oil, you have water, you have two pumps, which is very noisy and inefficient. So the new motor is smaller, lighter, more efficient, but also has just water cooling. So yeah, that's how we always try to improve stuff, and here we are testing it and running it through power tests and durability tests and stuff like that.
How do you actually test an electric motor? How do you run it?
It's actually quite similar to testing a combustion engine. So you have a load, which is the motor in this case, which can be a generator as well. And you have the motor and then power electronics underneath and a power supply. And the power supply, basically, when this is acting as a motor and this is acting as a generator, you have losses. So if both are running, so this is generating, let's say 100 kilowatts, this is running as a motor with 100 kilowatts, you basically just have to cover the losses of the system. So maybe you have to cover 10 kilowatts as loss. And based on the simulations you saw before, we have exactly the drive profiles. So for example, we can simulate a Nürburgring lap, and for the motor, it feels exactly like being on the track, except not having the vibrations and the G-forces, but the load profile exactly like it would be on the track. So for example, we can run here 0 to 100 acceleration or 0 to 400, or simulate 10,000 kilometers on a track or whatever, having the cooling system connected, having the right flow, the right temperature of the cooling system, the right voltage of the battery, you can simulate the environment of the motor exactly as if it would be in the car. And if you didn't have those simulations, you would have to guess this, or just have like set points, like run it at 10,000 RPM and at 100 kilowatt and just that. But since we have the simulations, we can exactly run it in the exact drive cycle as it would be in reality.
Wow.
We have a bunch of test equipment for batteries, temperature chambers, load machines, and battery emulators.
Yeah.
So we are testing cells, modules, and packs. So one of the things we are doing here, we are characterizing cells. So a cell is basically a chemical element, a chemical storage device. And in order to understand how the cell will behave and how the battery pack will behave, we are running a lot of simulations and a lot of cycles in different temperatures, different loads and so on, to have a mathematical representation of the chemistry and of the battery cell. So all of this is being done, so like you have to do this to get the input for the modeling.
Yeah.
So you know how the system will behave in given certain conditions. Here we have different departments, basically our industrialization department, which is making this transition of the company from small volume manufacturing to high volume manufacturing for other car companies. What's more interesting for you here is our autonomous driving team. So we are doing some interesting stuff.
Yeah.
So the car has over 30 computers inside, and the hardware and software for them, all of them we are making here, developing our own stuff. The only one which we don't develop on ourselves is the autonomous driving computer, which is basically an NVIDIA supercomputer running in the car.
Okay.
So that's a development unit. The actual production unit is smaller, so that's a really, really powerful computer designed for artificial intelligence applications.
Yep.
And one of the things we do, you can see it here, so one of the segments of autonomous driving is the like recognition of the elements. So that it knows, for example, in this case, where the track is, other objects like the fence or the grass and stuff like that, and this is being done in real time.
Okay.
So the car, the C2, has 9 cameras, 6 radars, a LiDAR, 12 ultrasonic sensors, and we are doing the sensor fusion and the neural networks to recognize the environment.
Okay.
And then, based on that, we can, for example, do path planning. Here we have an example of our path planning algorithms, which basically compare, here in this case, like a professional driver on a racetrack with our algorithm.
Okay.
And then we are trying to figure out, like, okay, what's the right thing to do, like how, what do you want, like, the car to simulate, like a Formula 1 driver or a drift driver or whatever.
Yeah, yeah, okay.
And then when you are on the track, when the user is on the track, the car can guide the user, which, you know, customer, an owner of a supercar might not necessarily have the skills to really use it.
Yeah.
So this is like to help the driver have like a professional drive coach sitting in his passenger seat and helping him and giving him perfect laps, him or her, perfect laps on the track.
That's really cool.
So that's the kind of stuff we are trying to achieve here. So this is really something quite special. We are developing an autonomous driving system for really high speeds, so like 300 kilometers and above.
Okay.
So a lot of things have to be done right, and like this is the system itself, but the whole car has to be developed completely differently in order to do this. For example, you have to have completely the ability to drive it by wire, so you have to have actuation in the steering, actuation in the powertrain and brake system. So if you have a hydraulic steering rack, you cannot steer the car. So you have to have an electric steering rack, but not just any electric steering rack, you have to have redundancy for the system. And you have to have redundant 12-volt system. You have to have redundant computers, software. So everything has to be. The whole car was so much impacted by this, which I also didn't expect. So developing the car from ground up to have level 4 function on the track was completely different than developing a car without this feature. So a lot of stuff happens around this to even make the car ready for the software. And then the software itself is a whole other game. We are here in our component engineering department. We have 70 people downstairs in vehicle engineering developing the car itself. Here we have over 200 engineers, not just in this location, but also the other location in component engineering. So all in all, we have over 300 engineers in the company. And here we are primarily developing components for other car companies, but also for our own cars. So I'll give you a few examples. Here in this sub-department, we are basically developing the control units, different kinds of electronics. In this case, for example, a battery management system master, which we use in other car companies' projects, but also in our own. Or here, an infotainment hardware. You can see like the connectors for the cameras and the antennas and screens and stuff like that. This is the screen with its own software, own hardware attached to it. And this is, for example, the control unit of the car, the vehicle control unit, which one of the things it's doing is calculating the torque vectoring algorithm.
Okay.
So it gets, like the stuff you saw downstairs running on the simulations is actually, the software is then running here. It gets all the inputs from the steering, from the braking, and having the algorithm on it to run it. Inverter drivers, like hundreds of different things. For example, the buttons on the steering wheel have their own little ECUs, the buttons in the car, the charger control, the inverter control, like hundreds of different basically computers that are running in the car. The hardware and software for that we are making here. But what this allows us to do is to have really a high degree of control over the system. So we can, with other car companies, this is mostly done by suppliers. So they have like a black box system for the infotainment, the black box system for the, I don't know, for the charger, whatever. Since we are doing most of it here, we can really be flexible and integrate it better and have more functions and more control over those systems. Here we are developing our powertrains. So the inverter, motor and gearbox. And it basically starts with the motor magnetics, so the active part of the motor. Then we have the thermal part of the motor, so cooling it down. Then the mechanical part. So this is, for example, the stator of the motor we saw downstairs. So we have the wires and the stator, and then the rotor comes inside and the cooling system around it and stuff like that. And here you can see basically the whole system together. So this is what we saw in the monocoque. So this is part of the monocoque, and the gearbox is in the middle, the motors on the ends, and the inverter on top. So we are here integrating everything together, but all the pieces like the inverter, the electronics is developed on the other side of the building, the mechanical part is developed here, the gearbox is actually developed here by these guys as well, and then putting it together. And the thing I said when we were looking at the car about making the trade-offs in space between the gearbox and motor and everything, like this is where it comes together, like how many millimeters do we give to the gearbox guys, how many to the motor guys, while still fulfilling all the requirements. Like that's always a fight.
I'm literally picturing those meetings right now, and how it goes back and forwards.
Luckily we are not a democracy. This is our battery engineering department. We are developing the mechanical part of the battery here, so the cooling, the battery modules, the connections, the structure of the battery, the housing, the wiring and stuff like that. The electrical part, so the battery management, is done in another department. And here we are actively currently working on, I think, like 15 cars for other car companies.
Oh, wow.
Like all the way, from the public ones like Hyundai and Porsche and Aston Martin and Koenigsegg and stuff like that. But also lots of really interesting stuff that we unfortunately can't talk about yet.
Stuff I can't pick for information about at this stage.
Not yet, not yet, sorry. We are very open when it comes to the stuff we do. I can show you everything. But when it comes to the stuff we do for other car companies, they are very close, so we can't talk about it yet. So unfortunately, we can't go too much into the details here, but yeah, interesting stuff is happening here. We are here in our design. This is Adriano. He's our head of design. So we know each other for 10 years. Yes, or even more. So basically he designed the concept one on his own. He was at that time working for Opel, right?
Yes.
In Rüsselsheim? GM. I was still in college and we did it over email. So he after work, I was doing it after college. I was responsible for the technical part, he was for the design.
Okay.
And now he's heading our design department, which is 15 people and I guess like 9 nationalities.
Yeah, something like that, yeah.
And I'll let Adriana say a few words, but just to give a high-level overview of design. So people, when they think about design, they think about something like this, like people do something
Sketches,
on paper, sketching, and magically a car appears. But that's like 1% of the process. Like that's really just the beginning. The design department is engaged in everything we do, in absolutely everything. Okay, of course the car itself, but even we do stuff here like the merchandise, our website, user interface for the infotainment,
the logo, even the
logo, business cards, stuff like that. And when we do, for example, infotainment for other car companies, we also develop the user experience here. Also, of course, for our own cars. But just to give you an example of the technical bits that we do here. So the designers are already considering like how to produce the parts, how to assemble them, the ergonomics, how you sit in the car. Or here, for example, as we were seeing downstairs, the simulations being done for the head impact. The designers here and the whole team here is working together with the engineering to get to an engineering solution that will fulfill the requirements. And sometimes it's really complex. Moving stuff around in the car, when you do packaging, like every millimeter you move something impacts 10 other things. So it's a lot of engineering the guys are doing here as well, but Adriano might explain it better.
Especially if we want to have some innovative features, like for example our knobs where we can calibrate the car, and this kind of features don't exist yet on the market, so we don't have a really good reference or not enough experience with the engineers that we have. Then we need to help them and also push our ideas that we have with our own simulations, with aligning with the engineers, and with having good agreements on how this actually then can work. Yeah?
Well, we've made it back to the showroom then. What a fantastic tour. Thank you very much for your time.
Thanks, Tim. And you haven't seen everything. You have seen a lot, but we have just moved our production of the batteries and the powertrain and wiring and upholstery to another location. We have several other R&D and production locations around Croatia and outside. And as you have seen, this is very cramped here, so we will build a new campus. So next time you come here, it will be hopefully quite different. And we have our bike company, which makes these high-performance electric bikes, which is next door, but we don't have time to go there now. So lots of stuff going on, but you have seen a big part of it.
Well, we've covered, I think, pretty much everything from some of the past of concept ones as well, and the final production going into assembly, seeing the early stages of the C2 and what's going into all the development, the simulations. It looks like you've got an awful lot going on from what I could tell. It's a very exciting time. Next up, the prototypes for the C2.
Yeah, then you'll get the ride, yes.
Well, that sounds very exciting to me for sure. Let's keep in touch about that 100%. Well, thank you very much again for your time. Appreciate it an awful lot. It's been a fantastic visit, and thank you for the opportunity to be able to bring everyone on to have a look around.
Thanks for coming, Tim.
Thank you. See you again very soon, I hope.
See you.
Well, there we have it. What an incredible visit. A huge thanks goes to Mate for showing us around. A truly special opportunity. And I hope you've enjoyed this full discovery here at the home of Rimac, exploring, learning about the behind the scenes, seeing what goes into producing cars like the new C2. I've certainly had an amazing time today. I'm not going to forget visiting Rimac, and I'm already looking forward to things in the future. So stay tuned, watch this space. A big thanks again to Mate and the team. What a location, what a place, what a day. That's it for now though. Thanks again, guys, and I'll see you very soon. Cheers.